Summation notation is something that's overly complicated. There's a pointer number. In this case, it's I. It's used to help us keep track of which object we're calculating at once. You know, what this is telling us is that we're going to do the same calculation multiple times. We're going to take each object's mass and each object's distance from the axis of rotation. We're going to square the distance and multiply by the mass. We're going to start with object 1. And we're going to go to each of the objects until we reach the last object. That's all this is saying. So for what we are about to do, there are 10 objects. So I'll be adding together 10 things. So the first thing, M1, it's located here, 5 centimeters away from the axis of rotation. So my first term will be the mass of M1. Well, the mass of M1 is 1/10 the mass of the whole meter stick. I took the whole meter stick. I'm breaking it up into 10 pieces. Is that okay so far? So next, I know that this piece is 5 centimeters away from the axis of rotation. So this represents the first term. I'm going to increment now and go to the second term. This was number 1, and this is number 2. So the next one. Well, how far away is it from the axis of rotation? Well, 10 centimeters plus 5 centimeters, so 15. I'm not sure a pattern is developing, but I believe I'm going to see a pattern here. They won't all have patterns like this. This does, because it's repetitive in nature. The shape is uniform, and we are breaking it up into equal sized pieces. All of that is necessary in understanding what we're going to do next. The relevant parts are, we're going to take an object and break it into pieces, and we're going to try and describe where each piece is and how massive is each piece. That's critical to what we're going to do next. So I go to the next dot, dot number 3. Right? So we're going to go from the first dot, which is the first 10 centimeters of the meter stick, to the last dot, which is the last 10 centimeters of the meter stick. And the first thing that I hope to focus your attention on is all of them have m over 10. So you can factor all of those out. And then all you have inside here will be the measurements for r squared. So 5 squared, 15 squared, 25, 35, 45, 55, 65, 75, 85, and 95. Squared, each one of those. Square them all, add them all together, and then divide by 10. And if done correctly, in centimeters, you get 3325 m. Now, we know that this is less than the actual value. But what I want to do now is I want to extrapolate this a little bit. The other classes, we got far enough where I suggested that they go home and try this for 20 pieces. And for you folks, you should try that. I'm not going to use a class time for it. We're already losing class time today for club, and I'm just a foul distemperament, but you should do it. It will give you a value that is closer to the right answer. But it's still not going to be the right answer for the same reason why estimating an integral by breaking it up into little rectangles doesn't give you the right answer, which is why they change, start doing trapezoids, or they start doing all sorts of weird things until they finally figure out how to do the actual math. There's something else here. This is a meter stick. it would be nicer if this was any rod or long object. Meaning it'd be nice to make this length L and break it up into 10 equal pieces. Choosing a meter stick means that I get to use something that's already a percentage. Meaning this first piece is 5 centimeters from the axis of rotation, 0.05 meters. That's also 5% of the length. Meaning I could apply this to any rod by saying that this is 0.05 L squared. You should consider what this would actually produce. It's not much different. I mean, I would just be putting a period here in front of every number, marking it not as a actual distance, but as a percentage of the whole length. And I'd be adding an L squared to all of them. Some of you are pretty shrewd. If I'm dividing each number here by 10 and then squaring it, it's like dividing the final number by 10,000. I'm sorry, by 1,000. And then adding L squared here. Ends up being the same. If I tell you that the length is 100 centimeters, we get back the original thing we just had. But now this works for anything that's much longer than it is wide or thick. You should try this for 20. You should go home this evening and give it a try. And I don't want to hear that your dog ate it. As funny as that might be for a person who doesn't own a dog. So I'm not sure I'm able to laugh at the joke today, but I'll do my best tomorrow. It'll be Friday tomorrow. So here's what I'd like to do. Exactly as I wanted. So I'm gonna come at it from a different angle. If I tell you that this whole thing has a mass of 20 kilograms and is 5 meters long, could you tell me how massive a 2 centimeter piece is? And I don't know if you can do this or not. I'm asking to see if you can. And I'm going to be patient and wait for an answer. So if you can do what I'm asking, fantastic. If you can't, no shame. So let's talk about our options here. If you did it as a ratio, you probably said 20 is to 5 as x is to 0.02. That's a ratio. The mass of the whole thing is to the length of the whole thing as the mass of a piece is to the length of a piece. It's not something I've taught you. You either came into my classroom with this capability or you didn't. You also could remember that density equals mass over size. You might have found the density of the object, which was 4 kilograms per meter. And realize that if I multiply this by its size, I'll get its mass. Does this seem familiar? If not, does this make sense to you? Because it's not complicated. And if you've never seen this before, I'm going to need you to be a quick study. Because this part's got to be the part that you step up to. It's not hard. So maybe another example, just to make sure we understand each other. We're talking about linear density here. mass per unit length. Guitar strings are sold this way. The G string and the E string are of different mass per unit length. They don't sell them like that because a lot of musicians don't need math, not like this, but that's what they are. Now, I need you to understand this concept. If you can't, then I'm going to need you to at least come up with a procedure that will satisfy what we're about to do. But ultimately, there are symbols that we tend to use for the different types of density, and they may come up. These are all Greek symbols. The top one is lambda, and they use L there for mass per unit length. So this would be the mass over the length. Then there's a sigma, which is supposed to be a circle with a little swoop on it. It's lowercase sigma, and it's S for surface, mass per unit area. And the last one is volumetric density. We use rho. I don't know what they used in chemistry. They didn't use a lot of Greek symbols in chemistry, but it's mass per volume. You see, they might not give you the mass of your object. They might just say that it's made out of this material, which has a density of lambda. You'll have to be flexible. But for the time being, I'm going to try and make this as straightforward as possible. So for the time being, you should tuck that information away, but it didn't work to use it in third period, and I'm afraid it's not going to work here. So I'm going to take away all of our placeholders and all of our numbers, and I'm going to say that I have a rod of length L, and it has a mass, capital M. And I want to find the moment of inertia about one end. This requires calculus. We could attempt to break this up into 10 or 20 or 50 equal pieces. We could, but we're not going to. We're going to try and figure out its actual moment of inertia. That's going to require a slightly different formula. Our sigma formula doesn't work. Our sigma formula requires that we have discrete pieces. However, I don't know how many pieces I'm going to break this up into. What calculus is going to do is it's going to allow us to make the size of the piece so small that the difference between the moment of inertia on this side and the moment of inertia on this side is nothing. So we're going to be making it very, 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 very thin. That's the promise of calculus. So you'll have to trust me that the process does that for you. The part where you perform the integral, it does that for you. It shrinks the size of the piece. So you're going to have to trust that that process does that, because I'm not going to explain that to you. You don't need to know that. That's where the fundamental theorem of calculus comes into play, and I really don't care about it. The hard part, though, the part that's not going to be taught to you in calculus, is how to set it up. You see, we have a formula for moment of inertia. And it's the same as the formula for the discrete moment of inertia. It's mass times r squared. Doesn't look that way because it's in the wrong order. Right? We've got the r squared here, and this dm is actually one symbol. That means a piece of the mass. That's what dm means. You know, it's really my objective to make a shirt for physics that somehow incorporates getting a piece of mass. I do understand as a physics shirt how awesome that would be if we could get that one snuck in under the radar. You hear it, don't you? Piece of mass. In there is something else, right? I know I can hear it. And I think if you talk about it correctly, we could get Ms. Freitas to approve it without really knowing that there might be a bit of a double entendre in there. Maybe. Maybe that's a little too overt. But I think it'd be kind of funny. So dm actually is a successor to saying delta m, where the Greek letter delta means change in, it also means piece of. So when I say delta m, I'm meaning a small piece of the mass. When I say dm, I mean a really small piece. That's the only difference between these two symbols, is that this is a small piece and that's a super small piece. So the symbology is no big deal. The fact that there's a D there is not a big deal. Now, here's the thing. Using this formula always requires that we somehow get rid of dm. Our job is to try and create an equation that is about the shape of the object. Now, it's going to be the hard part. So we have to change this. So it's not about the mass of the object, but it's about the shape of the object. But I've already kind of explained how we're going to do that. We're going to do that with a ratio. We're going to say the mass of the object is to the length of the object as a small piece of mass of the object is to a small piece of length of the object. That's what we're going to do. Now, there is a wrinkle to this, something that is troubling and will be tough. But I think we can overcome the wrinkle. You see, in order to do this correctly and to do this in such a way that we will be able to integrate, we need every variable that's in this function to be in the same terms. So I know you don't know what that means yet, but I'm gonna help you with that. First, I need to create a variable that tells me where this piece of mass is. And it has to be a variable that I can use to describe where the first piece is and where the last piece is. Meaning, I'm going to choose, I don't know what letter you use here, but I'm going to choose X because it's horizontal, just like a number line. I'm choosing X for a simple reason. We're all familiar with it. It's horizontal like a number line. And I think we can all agree that the first piece would be where X equals 0. And the last piece will be when X equals L. That when I look at this bar, I can break it up into lots of pieces, but the first piece will be right there at the edge. And the second piece will be all the way out on the other side. We good so far? Now, using this variable, I want to describe the size of this piece. How wide is it? And so I want to use this variable, and I'm going to say this piece is a distance X away from the axis, and this piece is just a little bit more along the X direction. I'm going to purposefully use X here and say that this, if I want to find out where this piece is, I walk out a distance X away from the axis, and this piece is a little bit more in the X direction. Is everybody okay so far? Now, that means that means that in this formula, the mass of that piece will be dm over dx. That's how massive this piece is. Are we okay with that? So that also means dm equals m over L times dx. In your notes, because I know I'm going to lose the bell here in a minute, what I want you to say is that this process expresses mass as a function of the size of the object. That's the first part of this. Express mass as a function of size. That's what we've done. So now we're going to build our integral portion of this. Our integral has 3 parts. Our first part is the piece of mass. Our second part is a variable that represents the distance away from the axis. And our last part tells us where to start and where to end. Okay? Now, we have just done the first part. We have found out what dm is. Our second part is to find out what variable would work best to explain how far away my piece is from the axis. Now, we picked a variable on purpose that would do that. It's x. So I'm just going to put x squared here. Now, I'm going to draw my symbol, and at the bottom of the symbol, I put where I start. And at the top of the symbol, I'm going to put where I end, where the last piece is. The last piece is a distance L away. Everybody follow me so far? All right. We have built the integral. Believe it or not, you've done all the heavy lifting. There's really not much left to do. So, everybody with me so far? Right, we might run out of time, but boy, I'd like to finish this. So we have I'm reorganizing this because now that we've built this, the next part has nothing to do with the problem. It's just doing the procedure for calculus. So the first procedure is to look at everything that's here. This variable becomes the most important variable of our problem. It's dictating what we do. We have an integral with respect to x. So because dx is featured there, that's how we say it. All right, we'll pick this up tomorrow. just say it again. I'm going to have a big rectangle of something. It's a big piece of wood. I don't know. It's huge. 4 by 6. 4 meters by 6 meters. And the whole thing weighs 64 kilograms. I'm going to break off a 10 centimeter by 10 centimeter square. How massive is that? Got to do this one a little different than the last time. Really trying to trip you up. Just want to get a handle on who's keeping up. So you put yours in the box. I want to walk by. Such a variety of answers. 64 is to 24 as m is to 0.01. Units are important here. So m equals 0.027. Now, you know that my next thing would be to do something in 3 dimensions, right? But I really don't need to go that far. You did the 3-dimensional ones in chemistry. And in chemistry, you had density equals mass over volume, and you did problems like this. I'm showing you that there's different kinds of density. This is something that has what we call surface density or areal density. So consider a piece of notebook paper versus a piece of cardstock. One of them has more density than the other, more mass per unit area. In the case of the prior question,